Okay, give me a second. Let's see where the bottom is. Oh, I'm still not so familiar with Zoom. I cannot seem to find the bottom.
Here, I'll just start sharing to actually kick you off.
Yeah,
I will
yeah.
actually stop sharing.
Thank you.
Sure.
So could you see my screen?
Yes, educational representation learning, and now you're in presentation mode. Proceed.
Okay. So hello everyone, I'm Hao Yang, and I'm a colleague of Guowei and Tao. I'm delighted to have this opportunity to introduce some progress in multimodal machine learning in educational scene. And in general, a modality refers to the way in which something happens or is experienced. We may associate the word modality with the sensory modalities such as vision or touch. And to understanding the world around us, artificial intelligence needs to be able to interpret and reason about multimodal messages. There's a wonderful survey paper on the topic of multimodal machine learning on TPAMI in 2019. And in this paper, it summarized 5 core technical challenges on multimodal machine learning. They are representation, that is learning to how to represent and summarize multimodal data, and translation to map data from one modality to another, and alignment, identify relations between elements from different modalities, and fusion, drawing information from modalities to perform a prediction, and co-learning, to transfer knowledge between modalities, their representation, and their predictive models. Multimodal machine learning enables a wide range of applications such as speech recognition and synthesis, event detection, emotion and media description, and multimedia retrieval. And each of them are relevant to 2 or more technical challenges. For example, in emotion recognition, we have acoustic signals, image information, and text. And to capture the interaction among different modalities, we may want to align image and speech signals to the text in the temporal domain, fuse these features to make predictions or learn a shared representation. Also, you may use text to improve visual representations for emotion classification by transfer learning, one of co-learning approaches. A first fundamental challenge is learning how to represent and summarize multimodal data. The heterogeneity of multimodal data makes it challenging to construct such representations. For example, language is often symbolic, while audio and visual modalities will be represented as signals. There are 2 categories of multimodal representation, joint and coordinated. Joint representations combine the unimodal signals into the same representation space. If you look at the figure on the left-hand side, you will see unimodal representation x1, x2 to xn are fed into a shared function or structure to learn a joint representation. Well coordinated on the right-hand side process unimodal signals separately, which means those blue dots and red dots don't share with each other, but enforce certain similarity constraints on them to bring them to what we term a coordinated space. Second challenge addresses how to translate or map data from one modality to another. Given an entity in one modality, the task is to generate the same entity in a different modality. There may be a number of correct ways of translation, and one perfect translation may not exist. Translation can be categorized into 2 types, example-based and generative. Example-based models in figure 2a use a dictionary when translating between modalities. And generative models, on the other hand, construct a model that is able to produce a translation. Figure 2b shows you that in the training stage, a model such as grammar-based model or encoder-decoder model learns from data and then translate data from source modality to target modality. The distinction between example-based and generative approaches is similar to the one between non-parametric machine learning and parametric machine learning. A third challenge is to identify the direct relations between sub-elements from 2 or more different modalities. For example, give a movie, aligning it to the script or the book chapters it was based on. As the figure shows, an event happened in T1 in modality 1 may be in correspondence to the event in T4 in modality 2. To tackle this challenge, we need to measure similarity between different modalities and deal with possible long-range dependencies and ambiguities. We categorize multimodal alignment into two types, explicit and implicit. In explicit alignment, we are explicitly interested in aligning subcomponents between modalities. For example, aligning recipe steps with the corresponding instrumental video. And implicit alignment is used as an intermediate of a latent step for another task. For example, image retrieval based on task description can include an alignment step between words and image regions. And the fourth challenge is to join information from two or more modalities to perform a prediction. And for example, for audiovisual speech recognition, the visual description of the lip motion is fused with the speech signal to predict spoken words. We categorize multimodal fusion into two types, model-agnostic approaches and model-based approaches. Historically, the vast majority of multimodal fusion has been done using model-agnostic approaches. Such approaches can be split into early and late and hybrid fusion. Early fusion integrates features immediately after they are extracted, often by simply concatenating their representations. For example, if you look at the figure, we concatenated audio feature, audio feature in blue dots and visual feature in green dots as input for the next layer. And late fusion, on the other hand, performs integration after each of the modalities has made a decision, for example, classification or regression. Finally, hybrid fusion combines the outputs from early fusion and individual unimodal predictors. An advantage of model-agnostic approaches is that they can be implemented using almost any unimodal classifiers or regressors. And now let's move on to model-based methods. Three categories of approaches are designed to perform multimodal fusion. First, multiple kernel learning methods are an extension to kernel support vector machines that allows for the use of different kernels for different modalities of the data. And graphical models are another family of popular methods, such as conditional random fields and factorial hidden Markov models. And finally, neural networks have been used extensively for the tasks of multimodal fusion. The general idea is fusing information in joint hidden layer of a neural network. First challenge is to transfer knowledge between modalities, their representation, and their predictive models. Co-learning explores how knowledge learning from one modality can help a computational model trained on a different modality, particularly when one of the modalities has limited resources, such as annotated data and noisy input. In parallel data in the leftmost figure, both modalities share a set of instances, for example, audio recordings with the corresponding videos. On the other hand, non-parallel methods don't require the modalities to have shared instance, but only share the categories or concepts. Non-parallel co-learning approaches can help with learning representations, allow for better semantic concept understanding. In a hybrid data setting, as you can see from the rightmost figure, two non-parallel modalities are bridged by a shared modality or dataset. For example, in the case of multilingual image captioning, the image modality will always be paired with at least one caption in any language. So here's the taxonomy of multimodal research we mentioned earlier. And we will now come to educational tasks with multi-modalities. A wide range of tasks are implemented in two stages. For example, in order to assign grades to written essays, first we convert images of handwriting to text with OCR, and in stage 2, machine learning models are trained to assign grades. Another example is classroom conversation analysis. To detect and analyze certain types of logic instructions, conversation tests must be extracted from audios by automatic speech recognition. And the second category of educational tasks are single-stage tasks, as data in educational scene, especially classroom data, is multimodal naturally. Multimodal data, including language, visual, and vocal data, will contribute to machine learning tasks together. For the sake of time, I will focus on the following 4 tasks: verbal fluency detection, dropout prediction, emotion analysis, and class activity detection. And some of them were mentioned by Zitao earlier. I will provide some technical details. Let's get started with spoken language proficiency. Spoken language proficiency is crucial for personal development. However, students in developing countries are too shy to express themselves or barely have chances to speak in classes, and as a result, fail to reach satisfactory levels of spoken language proficiency. So we created verbal fluency tasks, which allow students practice their oral language skill at home and develop Dolphin system to automatically provide feedback from 6 aspects, that is verbal fluency, topic relevance, vocabulary diversity, and post-interaction coherence and verbal emotion. Dolphin system helps students practice oral skill and at the same time reduce the burden of repetitive grading workloads for teachers. It's a multimodal task as the Dolphin system scores students' performance from their videos. And here's the overall workflow for verbal fluency. When a video clip arrives, we extract its audio track and transcribe it into text by ASR for phonological fluency scorer. In the upper side of the figure, we extract features from both audio tracks and ASR transcripts and concatenate them as early fusion, then feed them into a group-based neural network. As shown at the bottom of the figure, we also proposed a semantic relevance scorer to identify whether a student is talking about irrelevant topics, which uses a cross-multiple attention mechanism to extract the semantic relation between answers and questions, and then predicts a relevance score. Both offline and online experiments demonstrate the effectiveness of our approaches. So now let's turn our attention to students who drop off the class. In spite of the advantages of online classes, a large group of online K-12 students fail to finish course programs with little supervision either from their parents or teachers. It may be due to many reasons, such as lack of interest or confidence, mismatches between course contents and students' learning paths, or even no immediate grade improvements from their parents' perspectives. And therefore, it's crucial to build an early dropout warning system to identify such at-risk online K-12 students and provide timely interventions. We applied an early fusion approach to a distinguished set of features, which can be divided into 3 categories. The first is in-class features that focus on K-12 students' online behaviors during the class. And the second is out-of-class features that consider real-world factors happen after the class, which may influence the dropout decisions. And the third, time-variant features that include both historical performance of teachers and aggregated features of student activities within fixed size windows. All of these features are concatenated to train a grading boosting decision tree. In our offline experiments, our method improved the dropout prediction performance when compared to state-of-the-art baselines on a real-world educational dataset. And in online experiments, the results show that more than 70% of dropout students are detected by the system. And next, we will talk about emotions. Emotions are an integral part of a class and are experienced in teacher-student interactions quite often. Given a video of a class, facial expression and emotional voices can be captured. And on the other hand, sentiment analysis on what they speak may also provide clues for emotion recognition. Learning from multi-modalities will be beneficial as it captures the interaction between speech and the text. And here's the architecture of the proposed model on the right. The yellow part indicates the speech encoder, and the red part indicates the text encoder, and the blue part is the multimodal fusion network consisting of an attention network to fuse both speech and text modalities, and an LSTM is followed for sequential classification. And this architecture outperforms other existing methods on the IEMOCAC dataset. Okay, next let's take a look at the classroom activity detection. Here are some photos taken in our offline one-on-one class. There is one student with one teacher in the classroom, and the video is recorded with the recorder away from them to minimize its influence on teaching. In order to help teachers get instant feedback on their pedagogical instructions and improve educators' teaching skills, we need classroom activity detection, which focused on accurately classifying whether the teacher or student is speaking, recording both the length of individual utterance during a class, as you can see in the bottom of the figure. And it's also a multi-modal task, as we have data from both vocal and language modalities. The architecture shown in this paper, in this page, briefly illustrate how to distinguish what the student says from the teacher. First, the video is cut into many short segments, and we measure similarities between each two segments by their vocal features to cluster the segments. Then we can classify these clusters using text features of each segment extracted from a semantic embedding. The similarity calculation as well as clustering are implemented with an intention layer. This approach is able to outperform state-of-the-art baselines on classroom data. That's it. Due to limited data, maybe we can discuss some questions in the chat area. Please allow me to introduce the next speaker, Professor Neil, and he's an expert in assessment, and he will talk about algorithmic assessment and evaluation.